Okay, good morning. So this is our 26th session and today we will try to see the Navier-Stokes equations. So what we have done basically, we had put the hypothesis of Stokes in order to write our stress tensor. So that's why we are calling these equations and nothing but the Navier-Stokes equations. And the stress-strain relationship which we have developed, that is specifically applicable for Newtonian fluids. Okay, so that's why applicability of Navier-Stokes equations is particularly only for the Newtonian fluids. So we have this x momentum equation. So if you recall, then x momentum equation was nothing but rho into del u by del t plus u times del u by del x plus v times del u by del y plus w times del u by del z, and that was equal to minus del p by del x, and we were having some term plus del by del x of what was there. Okay, let me write first time del by del x of sigma xx del by del y of tau yx plus del by del z of tau zx. So please check it. Have I written it correctly or is there any issue? Is it correct? Please tell me. Yesterday I have told you. Okay. So now what we will do, we will substitute our stress tensor particularly in the right hand side. So now I will just put a equal to sign. Left hand side will be as it is, this entire term, and in right hand side I will be having minus del p by del x plus del by del x of sigma xx. Now can you tell me what was the value of sigma xx we derived yesterday? Sorry, this del p by del x was not here. Yes, this will also come later. Okay, so what was the value of del by del sigma xx? Minus p divergence of v, okay, plus 2 mu du by dx. So that is the value of sigma xx. Okay, then what is the value of tau ix? Mu times du by dy plus dv by dx. Okay, and what is the value of uh, mu times del w by del x? Sorry, I have written it wrongly, del v. So del u by del z. So this is our x momentum equation. So first we will try to simplify only this portion. Okay, so if I simplify this equation, what I can say is that p term I can take outside. Fine. So it will be becoming, once again left hand side I am not writing, minus del p by del x plus del by del x of lambda times divergence of v. Okay, and lambda also I can substitute now as nothing but minus 2 by 3 mu, because Stokes hypothesis also I am applying over here. So minus 2 by 3 mu times divergence of velocity vector plus, now we will try to do something over here. So what I will do out of this term, okay, let me first write it, del by del x of 2 mu times del u by del x plus del by del y of mu times del u by del y plus del v by del x. Okay, and then plus del by del z of mu times del w by del x plus del u by del z. So one important thing we will be now substituting over here, and that important thing is, we have already considered the Newtonian fluid. So for Newtonian fluid, viscosity will be, what will be viscosity? Constant. Okay, so the relationship between stress and strain is same. So dynamic viscosity will be constant. Okay, so I can take out this dynamic viscosity out of the integration. So if I do so, what I will be getting, once again I am not writing the left hand side, I will simply write minus del p by del x, and here this will be minus 2 by 3 mu I can take outside, and it will become del by del x of divergence of velocity vector. Fine. Plus, out of this we will get now important quantity. So mu I can take constant. So first, from the very first term, I can write it only I will take single del u by del x. So if I take single del u by del x, it will become del square u by del x square. Okay. Then from the second term I will take this first term. So this first term if I take, then it will become del square u by del y square, and third term will become del square u by del z square. Sorry, this one. Fine. Up to this, is it clear? Now what is left? One term is left from this side, so that I can write as plus del by del x of del u by del x. This is one term. Then this del by del y of del v by del x, it will become del square v by del x del y, and then this term del by del z of del w by del x, it will become del square w by del x del z, and with this entire term I will be having a mu outside. Point is clear? Is this one clear from where these terms are coming? So this was 2 mu del u by del x. 1 mu del u by del x I have taken over here, this term. Another mu del u by del x that I have kept here. Okay. And then this term was remaining del v by del x out of the second term. So that has become del square v by, because outside del by del y is there. So del x del y. Simply this z term also similarly, it has become del square w by del x. Fine. Up to this point, anyone is having any doubt? Okay. Now what I can do is I can again take minus del v by del x minus 2 by 3 mu del by del x of divergence of velocity vector plus mu times del square u by del x square plus del square u by del y square plus del square u by del z square. Okay. And plus, what I will do now, mu times del y del x I will take common outside. Okay. So if I take del y del x common, inside I will be getting del u by del x plus del v by del y plus del w by del z. And ultimately, what is this term? This term is once again nothing but divergence of velocity. Fine. All are clear with this idea? Okay. So the benefit of this is that if now I put the assumption of incompressible flow, if I now put the assumption of incompressible flow, what I will be getting? Divergence of velocity vector equal to 0. That is the conservation of mass equation for incompressible flow. Okay, so it means that my this term will become 0 for incompressible flow, as well as this term will become 0. Okay, so one very important point, while we have taken the Stokes hypothesis, we considered that lambda is equal to minus 2 by 3 mu. Okay, and I mentioned at that point that this particular assumption of lambda equal to minus 2 by 3 mu is applicable for majority of the flow situations except for extremely compressible flow situations where you are having the presence of shock wave, etc. There this hypothesis does not work well. Okay, so that is the reason, and another important point why this hypothesis is truly acceptable for incompressible flow is that because whenever we are writing incompressible flow, then divergence of velocity vector is becoming equal to 0. So this term which was having involvement of lambda, that is actually completely becoming 0, because for incompressible flow divergence of velocity vector has vanished. Okay, So that is the reason that for incompressible flow, even you can say that any value of lambda can work. If your flow is purely incompressible, though of course this value is having some relevance, that's why this is acceptable, but still for incompressible flow, because lambda is not playing any role, so that's why for incompressible flow our equation becomes very simplified one. Is this one clear? Okay, so ultimately, now if I have to write down the x momentum equation for incompressible flow, then it has become rho times, I think I did one mistake in the starting point. I have not put a bracket over here because rho will be with each and every term. Okay. So rho times del u by del t plus u times del u by del x plus v times del v by del y plus, sorry, del u by del y plus w times del u by del z. That has become equal to what? Minus del p by del x. For incompressible flow, this has become 0. This has become 0. So simply plus mu times del square u by del x square u by del y square plus del square u by del z square. So this is my continuity equation. Okay. So simply, sorry, x momentum equation. So here one simple thing you can do, if you take the square of your this del operator, and that if you take this u, then you will be getting this entire quantity. Okay. So this del square operator is called as actually Laplacian operator. Okay. So once I apply over here Laplacian operator, then ultimately I get actually all the terms which are involving the viscous stresses. Fine. Is this one clear? Anyone is having any doubt? Please tell me. And this is, I think you might have seen multiple times. This is a very simple equation which majority of the times we see. Okay, so appearance wise it is simple, but it still has complexities. So what are the complexities? That also I will tell you. But now similarly, can you write down the y momentum equation? Please tell me, what will be y momentum equation? Rho times del v by del t plus u times del v by v times del v by, please tell me fast. Now tell me what I will be having next. What will be next term? Simply del square v. Okay. Then what will be z momentum equation? Minus del v by del z plus mu times del square w. One term we missed yesterday, that will be nothing but minus rho g into k because of the gravity. So yesterday I forgot to write it in the z momentum equation because gravity is only acting in the z direction. Okay. Is this point clear? So it means that these are nothing but our differential form of Navier-Stokes equations, and the benefit of these equations is that if I solve these equations, if I find the analytical solution of these equations, so that will be nothing but a continuous solution. Okay, so I have variables u, v, w, pressure, etc. So if I solve these set of equations, then ultimately I will be getting some continuous function of velocity, u, v, w and pressure. So it means that whatever the solution out of this equation will be coming, that equation can be applicable for each and every point within the flow field. Okay, so that is the benefit. So integral approach was giving you a wholesome approach where you are actually getting the idea of properties for a complete total control volume. But what is happening at different point within the control volume at each and every location, that we were not bothering actually. Okay, but if we have to bother, so ultimately we have to bother, because whenever you will be finding that if you have to study the flow through a pipe, so in flow through a pipe there will be formation of boundary layer. At each and every point velocity will be different. That boundary layer will control your how much pumping power should be there to pump the fluid. Okay, so similarly if you are having aeroplane, if you are having automobiles, so for everywhere the principles of fluid mechanics will be coming, and we have to consider the variations of properties at each and every location. So once we are considering the variation of properties at each and every point within the flow field, then importance of the differential form of governing equation comes. Okay, because differential form is actually the, I can say from integral approach, this is the more advanced form. Okay, because it is giving us the solution at each and every point within the flow field. Okay, but what are the challenges with this equation? If you see this entire term of convective acceleration, what is this term? This term involving convective acceleration, it is nothing but a non-linear term. So mathematical difficulty is it's a non-linear term. Okay, and if you see the highest order involved in the equation is second order. So we have non-linear terms, we have second order terms. So finding out the complete analytical solution for a complex flow situation is not actually possible, feasible. So that's why what we have to do is the solution of this type of equations for very simplified situations is applicable. Analytical solution I'm talking about. Of course, other form of solutions, for example, with the advent of computers, nowadays we are having this computational fluid dynamics, and we take the help of CFD tools first to convert these equations into an algebraic set of equations which can be understood by the computers, because computers don't know partial differential equations, they can only do the algebraic operations. Okay, so in the approach of CFD, which is popularly called as computational fluid dynamics, so what we do there, basically first we convert these equations into the set of algebraic equations, and then we take the help of computers to solve the algebraic equations. So that way we can find out the solution of these equations for complex situations also. But that is not analytical solution, that's a numerical solution. Okay, so that's why that's not exact solution. Is this point clear? So difficulty with these equations is that these are having involvement of non-linear terms. Okay. Now another important point is, if you see these equations, these are the three momentum equations. Let's find the number of unknowns. So first unknown is u, second unknown is v, third unknown is w, and fourth unknown is, how many unknowns? 4. But number of equations? 3. Number of momentum equations? 3. So it means that this is not a closed form of equations. So if we have to close this equations, like if we have to make number of variables equal to number of equations, we have to always solve continuity equation along with the momentum equations. So I can say that continuity equation for fluid flow problems is nothing but integral part of the momentum equations. Because if you try to find the solution of momentum equation, you cannot find exact solution without having the solution of the continuity equation. Is this point clear? So whenever you are talking about the solution of fluid flow problem, you have to always consider the continuity equation. But one thing you have to remember, that whatever the form of equation now I have written, these equations are, what are the assumptions invoked? So first assumption invoked is Newtonian, second is incompressible. So these are applicable only for Newtonian fluids and incompressible. Okay. Mostly in this particular course we will be dealing with these two types of fluids only. Okay. Is this point clear? Now of course not today, but in the subsequent lectures, we will try to apply these equations for different kinds of flow situations, and then we will try to find out the solution of the flow field for the given situations. Okay, so that part also I will show you. The application part of these equations that I will cover in the subsequent lectures. But till this point, is it clear to you? Now comes one very important assumption. If I have in any situation, if I can consider that my flow is frictionless. So if my flow is frictionless, then ultimately the effect of mu will be vanishing. So if effect of mu is vanishing, then these terms will not be playing any role. So ultimately my equation, if I write in the vector form, I will write in crisp vector form. So if I write in the vector form, then equation will simply become rho times dv vector by dt. So this is the combination of this plus this plus this. These three together can be written as rho times dv vector by dt equal to, now this and this, del p by del x, del p by del y and del p by del z, all together in vector form it can be written as gradient of pressure. Okay, and then these viscous terms has become 0 for frictionless flow. So for frictionless flow, viscous terms are 0, and ultimately my only term will be coming is minus rho g into k cap. Okay, so this is nothing but a vector form. Of course, if I split it in x, y, z components, then I can write down the similar equation. And x, y, z component will be same, whatever I have written, except for this viscous term. Okay, except for the Laplacian term. If I remove, then whatever remaining is, that is nothing but the x, y, and z components of the equation for frictionless flow. Okay, so this particular equation is called as Euler's equation. So anywhere where you find that viscous effects can be neglected, you can get actually more simplified version of the equation. Okay, you need not to solve some of the extra terms which were particularly becoming the second order in your system of equations. Okay, is this point clear? Now the benefit is, so earlier you have seen that I have taken the integral form of the equation, and from that, when I applied that integral form of RTT equations, continuity and momentum, along a streamline, I was able to get the Bernoulli equation. This Euler equation is also applicable for a frictionless flow. So if I apply this equation for a streamline, and if I integrate this equation along a streamline, then also I will get nothing but the Bernoulli equation. So you can simply say that Euler equation is nothing but the differential form of the Bernoulli equation, or Bernoulli equation in other ways. So in more generic sense, I can say, because Euler equation is the generic one which is applicable at each and every point. So I can say that Bernoulli equation is nothing but special form of Euler equation. Okay, so this type of relationship you will be finding. So whatever we are trying to do over here is from different perspective we are trying to look at the problem, but ultimately the thing is same. The only difference is that this equation is applicable for each and every point in the flow field, but Bernoulli equation is applicable only along a streamline. Okay, is this point clear?
So this equation is applicable for any type of flow.
In frictionless flow.
Every type of frictionless flow, right?
Yes.
But Bernoulli is only for streamline.
Bernoulli is applicable, so in every type of flow there will be streamlines, but application of Bernoulli will be only along a streamline, along a single streamline. You cannot do one thing, that take a streamline, say in a flow field, you have flow field, say this is one streamline, this is another streamline. You consider point 1 over here, point 2 over here, and then apply Bernoulli equation. That you can do.
But for either equation we can do that.
Yes, because this is a generic differential form of equation. You can apply it everywhere. It will be giving you the field parameter at every point. Okay. Is this point clear? All are clear with this idea? Anyone is having any doubt? These are important equations. Okay. That's why I am taking time. Okay. Now Whenever we have to solve these equations, of course, these will require some sort of initial and boundary conditions. You simply recall, when you solve an ordinary differential equation, what you have to supply? When you solve ordinary differential equation, what you have to supply? You have to supply some value that at x equal to 0, y is equal to this, at x equal to l, y equal to something, or at t equal to 0, y equal to this. You give some sort of conditions, okay, then only you are able to find out the exact solution. Otherwise your solution will be with the help of some constant, arbitrary constants, okay. But if you have to determine the exact value of these constants, then you have to supply some boundary and initial conditions, okay. So typically we have to supply the initial and boundary conditions if we have to solve these, if we have to find the exact solution of these equations, okay. So typically for fluid flow, what type of situations can occur, that I will first specify to you. Say I can have a flow field something like this. This is my fluid medium, and say here I have some solid obstruction in the flow. So this is some solid boundary, and say this particular point is inlet of the flow, and this particular point is outlet of the flow, okay. So typically the involvement of initial condition will be required only when we are estimating the transient flow. And say this is my free surface. So I have some liquid, and this is my free surface, and here I am having gas, here I am having liquid. And I want to solve this liquid domain, how it behaves, okay. And say my coordinate system are, this side is x, inside is y, and this vertical direction is z. Fine. Is this point clear? Now, one important point, that when initial condition will be required, initial condition will be required only for the unsteady or transient flow. If you are having steady flow, then there is no involvement of the time, so that then initial condition is not required. Because what do we mean by initial condition? So whenever a solution is marching in time, we have to tell at t equal to 0 what is our physical situation, okay. So I can say that value of all the field parameters like velocity vector, pressure, etc., because right now I am only talking about the fluid mechanics, that's why I have written velocity vector and pressure only. If I consider the energy equation, then I have to write temperature field also, okay. So temperature field we will not be dealing in this course. So for temperature field, maybe in next year you will be having a course on heat transfer, there you have to deal with that, okay. So for velocity, for fluid flow, we will be having velocity field and pressure. So the values of velocity and pressure at each and every point within the flow, we have to specify at t equal to 0. That will be considered as nothing but my initial condition. Is this one clear? What I am trying to say over here? Okay. So how your solution is marching, that will depend upon the initial state of the solution. So initial state of the field variable. So initial state of the field variable, the meaning is at t equal to 0, I have to specify the values of velocity vector and pressure at each and every point, okay. Then comes boundaries. Now for different types of situations, we can have occurrence of different types of boundaries. But typically for fluid flow problems, you will be finding 4 different types of boundaries. One will be inlet, outlet. Say you are having a pipe. So some fluid is entering from the pipe and some fluid is going out of the pipe. So if you have to find the solution for that pipe, so you have to specify inlet boundary condition, you have to specify outlet boundary condition. Third thing, for a pipe, what will be happening? The entire solid surface of the pipe is acting as a solid boundary to the fluid flow domain. So this is nothing but a solid boundary. Okay. And third thing can be, if you are having an open channel flow, then in case of open channel flow, there will be liquid flowing, and above the liquid there will be some gas. Okay, so that is something which I have defined over here. This is a free surface. Okay, so these typically 4 types of boundary you will be experiencing in the fluid flow problems. Point is clear? Initial condition I have already told you. So if we are defining the values of field variable at boundaries and at each and every point within the flow field at time t equal to 0, that is called as initial condition. Okay. Now one by one we will go for the boundary conditions. So first boundary condition I will start with. First boundary condition I will start with solid wall. So if I have solid wall, it means that what is the meaning of solid wall? There will be impermeable boundary. It means normal component of the velocity will be 0, and because of the no slip condition, tangential component will also be 0. Or in other words, I can say in more generic sense, this wall can also have some velocity. Say if V wall is the velocity of the wall. Okay. So ultimately, if V wall is the velocity vector of the wall, then I can say that V fluid will be equal to V wall at the junction. Is this point clear? So whatever is the velocity of the fluid, that will be the velocity of the velocity of the wall, that will be the velocity of the fluid at the junction. Okay, is this point clear? So this will be the boundary condition, and this boundary condition will be applicable for all the times. Okay, so it does not mean that at initial times or later times only this boundary condition is applicable. This is applicable for the complete duration. Okay. Then you have inlet and outlet. If you have to find the exact solution, then you must have known values of velocity and pressure for inlets and outlets. Okay. So at inlet and outlet, we must know a priori the values of velocity and pressure. Is this point clear? And later on, whenever we will be doing the solution, we will be finding that exact value of pressure or velocity is not needed for both the walls. Rather, one is required, and for other also we can calculate it by just considering the gradient of that boundary to be 0. So how that helps, that we will see while we will be doing the solution. But one important point is we must have known values of velocity and pressure across the boundaries. Okay, for inlet and outlets. And then we have free surface. Now can you tell me what conditions are needed to specify boundary condition at the free surface? So if you only want to solve the liquid portion, you don't want to solve the gas portion, then you have to supply some boundary condition which is acting at this surface. First, let me define that this free surface variable z is a function of x, y and t. Okay, so eta is representing some function of x, y and t. Of course, with this different x, y and t directions, this free surface can have different profile, and at different times also this free surface can have different profile. Okay, so one important condition which will be existing at this free surface, I can say that this free surface is say moving in the, if any upward velocity is there within liquid at the free surface, what I will be finding? I will be finding that the gas immediately above this will also move with the same vertical upward velocity. Is this point correct or not? If you say that in vertical direction, gas and liquid are moving at different velocities, then you will be getting some wide space at the free surface, which is not feasible under the practical circumstances. So it means that when your free surface is rising up or down, so with whatever velocity free surface is rising up or down, with the same velocity the gas above or below will be having same vertical component of velocity. So this is, I am referring only to the vertical component of the velocity. That's why I will be writing over here that W component of gas must be equal to W component of liquid at free surface. This point is clear? So this is the first boundary condition, and this is called as kinematic boundary condition. This is called as kinematic boundary condition. Okay? Is this point clear? Then second boundary condition I can have is this liquid and this gas will be having some interfacial shear. This will be having some interfacial shear. Say I have some tau on plane Z in x direction, tau zx. So similarly, equal and opposite amount of shear will be there in the gas part. Okay, so I can simply say over here that tau zx in gas will be equal to tau zx in liquid. This is one shear stress, and on the same Z plane other shear stress will be into the board. So that is y direction. So it means tau zy in gas has to be equal to tau zy in liquid. Point is clear? So this is the other boundary condition which will be applicable at the free surface. One is normal velocity has to equal, other is shear stress has to equal. If shear stress is equal, then only interface can stay at its equilibrium position. Okay. Then third boundary condition is that you know that from the top there will be some fluid pressure acting on this. So this will be the pressure of gas, and some pressure is also exerted by liquid. Okay. And then we have this curved surface also. And at curved surface, if we consider the surface tension, then there will be some interfacial tension force also. Is this point clear? So we know that now this is a two-dimensional surface. So for this 2D surface, if I take x and y as two principal directions, then I can say that if my Rx is radius of curvature in x direction and Ry is radius of curvature in y direction for this free surface. Okay, then I can write my gas pressure is equal to liquid pressure minus coefficient of surface tension times curvature. Okay, and that curvature will be becoming equal to what? 1 by Rx plus 1 by Ry. This will be the third boundary condition of the free surface. Is this point clear? How I have written this condition? This is simple, identical to that of a bubble, drop. When we have a bubble, when we have a drop, when we have a cylinder. So what we do? We calculate first the curvature. Curvature is nothing but we have to consider the two perpendicular axes, and along these two perpendicular axes, whatever our radius of curvature is there, if I take inverse of that and add, that will be my curvature. So curvature of free surface when multiplied with surface tension, that gives the difference of pressure across the boundaries of the interface. So that's why I am writing P gas equal to P liquid minus gamma times 1 by Rx minus 1 by y. Okay, so these are the generic set of boundary conditions which will be mostly applicable for fluid flow problems. But of course, whenever we will be applying these to different situations, then these boundary conditions can come with their different variants. So how the different variants of these boundary conditions will be coming into the actual flow situations, that we will be seeing in the subsequent lectures. Okay, over here the whole idea was to introduce you that in order to solve the equations which we have derived, we have to supply initial and boundary conditions, and out of these boundary conditions, what are the common physical scenarios which we can observe in case of fluid flow problems, and how these physical scenarios can be mathematically modeled. Is this point clear? So all are clear with the idea of equations. Now next equation which we have to consider is energy equation, but of course, as I told you, because that is beyond the scope of this course. We will not be dealing with the temperature field in this course, so that's why I will not discuss it over here. That probably you will study in your heat transfer course. Now we have one more important quantity which actually helps us in reducing the number of variables and number of equations which we have obtained over here. Okay, and that quantity is actually driven by taking the advantage of mathematical parameters. So that is called as stream function. And this stream function is represented by parameter psi. Okay. So basically if you see, and one important point, okay, that I will tell you later. Let's consider our incompressible flow situation. For incompressible flow situation, incompressible, and second assumption I will make 2D flow situation. So if I consider incompressible and the 2D flow situation, what will be my continuity equation? My continuity equation will be del u by del x plus del v by del y equal to 0. So this will be continuity equation for two-dimensional incompressible flow. Okay. Now, if I consider a mathematical operator in such a way so that this equation is completely satisfied. Okay. What I can do, I can consider any scalar quantity psi. So I have considered any scalar quantity psi such that u component of the velocity is equal to del psi by del y, and v component of the velocity is minus del psi by del x. Now if I substitute this formulation over here, what I will be getting? Del square psi by del x del y minus del square psi by del x del y equal to 0. Point is clear? So the meaning is, if I consider that u is equal to psi is some scalar function and u is equal to del psi by del y and v equal to minus del psi by del x, then mathematically this function, this formulation is actually inherently satisfying the continuity equation. Point is clear? So if it is inherently satisfying the continuity equation, once I am using this formulation, I need not to solve the continuity equation. Is this point clear? I need not to solve the continuity equation for any flow field, because if I am using this formulation, then ultimately continuity is inherently satisfied. Okay. Second advantage of this is that this particular formulation is actually helping us. How it is helping us? It is helping us in representing two variables u and v in terms of a single parameter psi. Okay, so that is the another advantage. Is this point clear? The second advantage of this is, now your u is also represented in terms of psi and v is also represented in terms of psi. So it means that if you put this particular formulation into your momentum equation, in your momentum equation u and v will be replaced with a single parameter called as psi. So number of parameters has reduced. Is this point clear? What I am trying to say over here? Okay. So this type of function which helps us in reducing the total number of parameters, okay, and which inherently satisfies the continuity equation, that is called as a stream function. Okay, this is called as a stream function. But one important point you have observed over here, that this stream function I was only able to define for a two-dimensional. Okay, so if I have to now write down the vorticity vector, so of course for 2D flow vorticity component will be coming only in z direction. Okay, so my vorticity vector will be becoming del z component of vorticity will be becoming del y del x of del v by del x minus del u by del y, which ultimately, if I now replace this v with minus del psi by del x, it will be becoming minus del square psi by del x square minus del square psi by del y square. Ultimately, I can take minus common. It will be becoming del square psi y del x square plus del square psi y del y square, which is nothing but for a 2D situation Laplacian of minus del square psi, Laplacian of psi. Okay. Of course, I must put over here k cap because I am only talking about the z component. Sorry. Okay. Is this point? Yeah. So vorticity field also very precisely we were able to write in the form of string function. Now, this formulation whenever I have discussed for the psi, this I have discussed for incompressible flow. Now, another beauty of this function is that value of psi remains constant along a streamline. How we can prove it mathematically? So we know that what is the equation of streamline? Please tell me. What is the equation of streamline? Equation of streamline. Dx by u equal to, for 2D flow it will be this one. Okay. So from here I can write u times dy minus v times dx equal to 0. This is the equation of a streamline. If I replace u with del psi by del y into dy minus v times, sorry, minus minus will become plus del psi by del x into dx equal to 0. What is this? This is total derivative of psi. So d of psi has become equal to 0. So when I am substituting this formulation into equation of streamline, then d of psi is ultimately becoming equal to 0. The meaning is that psi is equal to constant. So it means psi is equal to constant along a streamline. This is the another advantage of this method. Fine. Is this one clear? So now more details about psi we will discuss in the next class.